Hello everybody, this is Dr. Weber. This is the first of many lectures that you are going to have during the course of this semester. I'm going to record them and then you'll watch them on particular days, progressing through as if we were actually in class together, doing our lectures together, and then you'll be working through a set of what I call engagement checks, which are active learning activities. Essentially, you learn the material here by watching the video with me, and then you practice it by working through a little activity or by answering a short question that I have that covers the material that we just covered in the few minutes before that, okay? And so let's go ahead and get started. This first one is covering parts of chapter 1 in your book. And this first little mini lecture I'm calling The Nature of Science. If you watched the video that I encouraged you to watch in your reading quiz, which I highly encourage you to watch those Crash Course Astronomy videos, you will have seen a little bit about what astronomy is and what we do within astronomy. And then you will know that astronomy is constantly changing all of the time. And that's a really cool thing about astronomy, is that we're learning new things every single day about our universe. And so that means that sometimes a slide that I might present one day, I'll have to review and we'll have to change it because we learned something new. And then we'll have to revise our understanding of the universe. I think that's really exciting because it means that astronomy is constantly keeping itself fresh and new. We learn more about our universe as it evolves, as we have new techniques and instruments that become available to us. A lot of engineering work and computer programming work goes into that. And we learn more about our universe as we extend our observations over longer and longer periods of time, which allow us to look further and further back to the beginning of our universe. Science learns just like we learn. Over time, we hope that we get closer and closer to the actual reality of what's happening in our universe. So there are 3 fundamental hallmarks of science that I want to talk about here. This isn't specifically in your textbook, but I think it's important to highlight. The first hallmark of science is that modern science, the science that we have happening right now in our world, seeks explanations for observed phenomena that rely on natural causes. So we see something and we have to come up with a way to explain that through scientific laws, through theory, through test and practice. And we can't invoke things like divine intervention, our own personal beliefs, and our own personal opinions to help us make sense of science. Sciences are facts, or at least something that we've observed to be true, but we revise that knowledge over time. The second hallmark of science is that we progress through it with the creation and testing of our models of nature that explain our observations as simply as possible and with the fewest number of assumptions. We want our answer to be elegant. I'm going to say that we want our answer to be elegant. The simplicity sometimes is referred to as something called Occam's Razor. So what do I mean by Occam's Razor? Well, there was a fellow named William of Occam who lived from 1285 to 1347 AD, and this idea is named for him. And this idea says that when presented with competing hypotheses, these are educated guesses, that make the same prediction about something that we observe, one should select the solution with the fewest number of assumptions. We want the thing that's simplest, the thing that's the most elegant. And in particular, Occam said that, and this is a quote directly from him, more things should not be used than are necessary. So we're going to go through a few examples of what that means. So here's a great example of Occam's Razor applied to our solar system. Here, this first figure is a depiction of what's called the Ptolemaic system for our solar system, and it is a geocentric system. This system and the philosopher Ptolemy suggested that the Earth was at the center of our solar system and that everything else orbited around our Earth. The Earth was the center, everything else orbited around it. We have the sun being way out here, Mars, Jupiter, Saturn, etc. And in order to make sense of what he observed with the motions of the planets in the sky, they had to invoke something called epicycles. And so an epicycle was, imagine that you have your planet orbiting in a concentric ring around the Earth, but then that planet is also orbiting in a little baby orbit around that same orbit too. So it looks like it's kind of wobbling in the sky. And so they had to invoke these things called epicycles to explain the fact that sometimes planets are observed in our sky to, instead of progress in one direction, to sometimes change direction for a little bit over the course of a few nights or maybe a few weeks, and then turn around and go back again. We call that retrograde motion. So in a geocentric system of a solar system, you can only explain that by invoking these things called epicycles. However, we get later Copernicus, who comes up with this idea. Well, he wasn't the first person to come up with this idea, but he again suggested that actually maybe it's not the Earth that's at the center of our solar system, maybe it's the sun. If you invoke the model of the heliocentric system, which means that the sun is in the center and all the planets orbit around the sun, then you don't have to invoke this complicated epicycle system, and everything just makes sense if you assume that the sun is the center and all of the objects are orbiting around it. So Occam's Razor applied to the situation would tell us that we don't want to invoke these complicated epicycle systems. Everything would be much simpler if we assume that the sun is the center of our solar system and all the planets then move essentially in a concentric circle around the sun. But we'll learn more later about why planets don't actually orbit in a perfect circle around the sun. Now, the third hallmark of science is maybe what I think is maybe the most important, is that a scientific model must make testable predictions about natural phenomena, events that occur in our universe, in our world, that would force us to revise or abandon that model if the predictions did not agree with those observations. Sometimes these predictions that we make require us to invent new technologies. Because we make a prediction, we don't necessarily have to be able to test it immediately. Einstein made many predictions that couldn't be tested until after he passed away. So we have to think about ways in which we could test our predictions, and hopefully we can do that now, or someday in the future someone will have the technology to be able to make sense of those predictions. So science is not just a body of knowledge. In astronomy, we're not going to just learn facts. We're going to learn methods. Science is a method by which we attempt to understand nature and how it behaves. And we use something called the scientific method in all sciences, not just astronomy. And the four big pieces of the scientific method are observations, experiments, models, and testing. Here's a flowchart for our scientific method. First, we observe something that we don't understand. We get as much data as we can about it. We collect a lot of information. Then we ask a question about those observations, something that we want to know about those observations. Then we form a hypothesis. A hypothesis is an educated guess based on all the knowledge that we already have. And this hypothesis must be something that we can test. Maybe if not now, maybe sometime in the near future. And then we make a prediction based on these hypotheses. And then we perform an experiment or a test to see if we can make sense of these predictions. We experiment or perform additional observations in order to test this prediction here. Okay, and then we'll have outcomes. We revise our hypothesis and make additional predictions and tests based on our outcome. So let's say that our test supports our hypothesis, our educated guess. Then we can make additional predictions and test them and just keep on going. But what if the test we performed did not support our hypothesis? Then we have to think, maybe we have to change our hypothesis. Science is always changing. or maybe we make another hypothesis. We can revise it, we can tweak it a little bit, or we can just abandon it altogether and try again. So here's an example of scientific method applied to an everyday situation. Let's say I go out to my car and the car won't start. This is my observation. And my question is, well, why won't my car start? So that's the most important question I want to ask right now. And then there are a bunch of different hypotheses you can make about why your car doesn't start. But my hypothesis is going to be that, well, the battery in my car is maybe dead. And then I'm going to make a prediction. I bet that a jump start will start my car up. Then I test it. I actually try to jump start my car to see if my hypothesis was correct. And then if it turns out that the jump start did restart my car, my hypothesis is supported. And I could make additional predictions if I wanted to, but hey, I just want to get to school, so I'm good to go. But let's say that I tested my hypothesis, I jump started the car, and that didn't turn my car on. My hypothesis was not supported. Well, then I have to figure out, well, there must be a different reason why my car wouldn't start. I have to revise my hypothesis. So maybe instead, if the battery wasn't dead, maybe I forgot to fill up the car with gas the night before. And then I could check that and make a prediction and test that to see if that was the cause for why my car didn't start. Okay, so that's an example. And here we have the scientific method applied to astronomy. That's what we do all the time within astronomy, using the scientific method. Our observation is that Betelgeuse is behaving really unusually. Why? And our question is, why is Betelgeuse behaving so unusually? Okay, let me explain to you what I mean. So Betelgeuse is a star, and Betelgeuse is usually one of the 10 to 12 brightest stars in our sky, in our night sky. This is what we call a light curve. It's the light from Betelgeuse over a period of time. And here we have units of magnitude, which we'll learn more about. Magnitude is how bright the star is, and it's a little counterintuitive, but the smaller the number here for the magnitude, the brighter the star is at that time. So we see that Betelgeuse, over the course of many years, starting from 95, this graph goes, fluctuates in its brightness periodically. We know that Betelgeuse does that. Betelgeuse is a supermassive star, and it has been known to fluctuate in its brightness over time. But then something very weird happened in the winter of 2020, in the winter of last year, and actually the fall of 2019 into the early 2020. Okay, and so we saw that Betelgeuse's brightness decreased substantially, such that it was no longer one of the 12 to 10 brightest stars in the sky. And so our question was, why was Betelgeuse behaving in this way? We observed the light curve. Why is it doing this? And the hypothesis, there are many hypotheses, but one of those hypotheses is that Betelgeuse is about to explode in a supernova. So a supernova is the explosion of a massive star at the end of its lifetime. Now, Betelgeuse is a very massive star. This is how big Betelgeuse is compared to our solar system. It is really so massive. So here's our sun in the middle, and then this is the orbit of Jupiter, and then the orbit of Saturn. So you can see in this extended spot, that's the size of Betelgeuse. So you can see how large it is compared to our solar system. So the hypothesis is that Betelgeuse is going to explode in a supernova. Well, it turns out that Betelgeuse did not explode into a supernova. And so this is more recently the light curve coming from Betelgeuse. We see that so this one starts in 2018, and we see that it did dip in its brightness for a little bit, came back up in early 2019, and then very quickly started decreasing in its brightness through late 2019, reaching a minimum in its brightness here in early 2020. But then we see that now its brightness is ramping back up again, such that it's about on par with what it was in early 2019. Okay, so it didn't go supernova, it didn't explode, but why did Betelgeuse have such a large dip in its brightness? It's somewhat unusual. So our hypothesis that Betelgeuse was going to go supernova is not supported. Okay, you could have made a prediction that we will continue to observe Betelgeuse fluctuate in its brightness, and it may even get fainter as it approaches the end of its life. That's assuming that you're still operating under the hypothesis that it would go supernova. But we tested that prediction by observing the star for a longer period of time and found that that hypothesis that the star would go supernova was not supported. So we have to iterate. We have to come up with a new hypothesis for why Betelgeuse was behaving like that. And there are many hypotheses that have been proposed, but still, astronomers still are not fully agreeing on what was the cause of Betelgeuse's extended dip in its brightness. We know that it wasn't because it went supernova, because it's still there. And so one idea was that maybe there was a giant cloud of gas and dust that passed in front of Betelgeuse to diminish its brightness for a period of time. Another one was that maybe there were star spots on the surface of Betelgeuse. Star spots are dark patches on a star's surface caused by extreme magnetism. We'll talk more about that later in the semester. Maybe it was a Death Star, like in Star Wars, passing in front of that star. Maybe an alien civilization has figured out how to create these sorts of things. Or maybe it's giant convection cells. Now, stars are made up of hydrogen and helium. That gas is really hot. That gas sort of bubbles around inside. You can think of it as being kind of like when you heat up a pot of water on the stove, how the hot water at the bottom rises to the surface. It makes those like billowing kind of pillow patterns, and then it turns over and falls back down to the bottom of the pan again. So this is a simulation of what might have been happening on Betelgeuse, that it was getting so hot that all this material was bubbling around on Betelgeuse, and then you got these extended dark patches, which are cooler parts of the star that have risen to the surface and are cooling. Maybe it was these dark patches that lived for a very, very, very long time on the surface of Betelgeuse that was causing these extended brightnesses. So we don't quite know the cause yet, but scientists, astronomers, astrophysicists are continuing to work to try to understand it. What do? You continue to observe that star for a long, long period of time, maybe in many different wavelengths of light, many different colors of light, and see if you can, make a new prediction.